Okay, let's get the show on the road, huh? Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Hopefully you guys are doing good. I, on the other hand, am wondering, what did I get myself into? Why did I sign up for this? It's way too early. But we have to get the spread, so let's actually do it. Going into a new phase, phase 3. And let me make sure I can see the chat here and everything. Yeah. And sure. If you're not too sleepy, you can turn your cameras on and let's actually get through it. Yeah. Okay. So hopefully you guys are doing well. It's the first time I'm actually seeing you guys in the morning. I don't know how you guys are, if you're morning people or night people. Maybe this was the trick. Maybe you guys will actually talk to me more now. Yeah. On the other hand, I'm kind of weird. I've been good with sleep recently, which is a big deal for me. I've been getting close to 8 hours 3-4 days a week now, and I'm getting like 6 or 7 the other days, which is like literally amazing. But yeah, I've been working on my schedule. Everything is going well. I've noticed recently my REM sleep has been going down, though. I think it's just anxieties over the end of the semester. I have a lot more things going on than usual. I know you guys are the same. You're students. You're doing some of these for the first time. So I totally get it. Totally get your anxieties. We will work through this together. Just don't give up. Don't lose faith. And keep going with the plan. So I've put plans in effect. Some of them work well. And then other issues arise. You take it in stride. So right now, I'm obviously going to have to find some way to reduce my stress a little bit more to get actually restful sleep, because that is actually also important for learning as well. Like your brain, you'll learn better when you sleep better also. So don't think of getting a lot good sleep as something bad, something you should always strive for. I mean, when you're young, you can kind of get away with a lot of it, but the older you are, the more lacking in sleep will catch up to you. And especially if some of you, I believe, are student athletes, you definitely want to make sure your sleep is in check. That being said, let's move on. Kind of stumbling here. Let's see if I remember how to write this early in the morning. We're going to move on to another phase, which is polar coordinates and parametric curves. We're going to do parametric curves first, because you can actually think of polar coordinates as a subsection of this field. And in this section, I'm also going to talk a little bit about conic sections, but nothing in detail, pretty much sketching. I'm going to remind you guys how to sketch hyperbolas and sketch ellipses and things of that sort, if you didn't remember. Pretty much, right? So conic sections would include parabolas, circles, ellipses, hyperbolas, but most students forget about ellipses and hyperbolas and how they work. So I wanted to remind you guys of that as well. That's going to be important for sketching in multi. So we'll also do that in this section, but I didn't think it was a big enough deal to actually put in the title. But we're going to do something extremely, extremely important, the idea of a parametric curve. And when you go into multi and higher mathematics, you're going to realize that dealing with vector functions are going to be a lot easier, a lot nicer in many cases than dealing with the functions that we've been thinking about regularly. And in order to understand vector functions, you'll have to understand this idea of a parametric curve, parametric curves. So that's what we're going to do. So it's going to, like I say, be very introductory. We're just going from the basics and building up. And pretty much everything else we're doing from the for the rest of the class is going to be like this. It's like I'm going to introduce something totally brand new and build it up. So we're not going to get very far. It's not going to get too complicated. We're just wanting to learn these topics. So it's not like when it comes to integration, was a continuation of something you already knew. No, here we're starting from the scratch. All right, so we're used to seeing curves in what we call scalar form. So now I'm starting. So here's the first sentence here. We're used to seeing curves in what we call scalar form, right? So that's basically an equation with x's and y's in it, right? Maybe some constants. So for example, y equals x cubed. So we see that equation y equals x cubed, and most of us know what that's about. That's like, of course, the cubic. That describes this function, one-to-one onto function, right? And we might see the equation x squared plus y squared equals 4. And yeah, that gives us, as I'm sure you guys know, a circle with radius 2. And center the origin, right? So these are called scalar equations, just equations with x's and y's. Now, occasionally, here's the thing. We want to isolate what the x and y's are doing. So this is an equation that tells me x and y combine to do this thing. Sometimes you want to actually know, you know what, forget about the y, just focus on the x's. How are the x coordinates behaving? And forget about the x's, focus on the y's. How are the y coordinates by themselves behaving? So pretty much what we do is we separate the x's and y's, and we come up with different functions that describe what the x coordinate is doing by itself and what the y coordinate is doing by itself. We want to be able to talk about these guys independent of each other. How we actually do this is we come up with some other variable. This variable is called a parameter. So customarily, when we first introduce this, we often use the parameter t. So that's what I'm using here. Some other variables, say t. And t is very commonly used because it's often thought of as time, right? So it's a very basic use for it. So you'll see it in physics a lot. A lot of times the variable is going to be t that you're thinking of x and y in terms of, because it's time. But it can be much more general than that. So I come up with some other variable t, and I try to describe the x coordinate as a function of that variable and the y coordinate as a function of that variable. So I want to talk about over time, for example, how does the x and y behave independent of each other, right? So this is like I'm coming up with functions that describe the x and y. Now, this is something we've actually seen before. And you might wonder what would be the point of doing something like that, but we've actually seen it. We've seen this before. Yeah, I can't even write properly. It's so early. Where have I seen something like this before? This is the first time I'm hearing about parametric equations. Well, trigonometry is where you saw it before. Way back in pre-calc, let me take you back, Throwback Friday. We saw that when we looked at the unit circle, we wanted a way to track the x and y coordinates separately. And we decided to track these in terms of the angle that was it made with the positive x-axis, right? So we had the unit circle, and we decided, you know what, let theta be a variable that measures the angle here. And then there's going to be a coordinate here, which of course is the xy coordinate on the circle. What we're going to do is we're going to track x and y separately. We invented a function to track the x coordinate. This function was called the cosine. And we invented another function that tracks the y coordinate. This function was called the sine. And so basically what we did was we set up x is equal to cosine theta and y is equal to sine theta. Here, theta was your parameter, right? These guys here were therefore called parametric equations. Right? Now, they weren't introduced as such at the time, but at this point, you should start to appreciate what the power of this is. By doing this, we literally invented an entire branch of mathematics, trigonometry. We really figured out what the cosine and sine looked like. We were able to graph them. We came up with the other trig ratios. We came up with inverse trig functions. From that, we could develop trig substitution and a whole bunch of other things, hyperbolic trig functions. like a whole host of mathematical knowledge came out of this one idea. Let's track the X and Y coordinates around a circle separately. We instituted a parametric equation where in this case, the parameter did not represent time, it represented an angle. And we literally use these two parametric curves to build up an entire branch of mathematics. So parametric equations, it's a really powerful thing. Sometimes when you sort of have a big problem, lots of things are going on, but you decide to, break it into smaller things, just focus on one thing at a time, amazing things can happen, right? Not just in life, but in mathematics as well. So this is an idea that we have seen before, even though it wasn't introduced as such. What I'm going to do now is sort of talk about this kind of idea in general, like when we separate x's and y's and talk about them in terms of other functions in general, what are the sorts of things that can come out of that? Now, with very specific kinds of parametrizations, you can really just build an entire theory on these, and it will actually work out. So now let me actually write the definitions just to get a little bit more precise on this. I was kind of talking about it in a very fuzzy way, right? Suppose I can define x and y by functions, x equals x of t and y equals y of t. The variable t is called a parameter. The equations x equals x of t and y equals y of t are called parametric equations. Now, of course, you can actually sketch these guys, and the sketch of it is called a parametric curve. If you put limits on your parameter, your variable, you will have that the lowest point of the variable will give you what we call the initial point, and the highest point of the parameter will give you what we call the terminal or the final point. Okay. So the graph you get from a parametric set of parametric equations going from the initial point to the terminal point, that is called a parametric curve. Now, it's worth mentioning that you do not have to bound the parameter by finite numbers. You could let it go from negative infinity to infinity, and you can keep going forever in all directions. And it doesn't mean that you go off forever, because even in the case of the circle, even if I allowed theta to go off to infinity, it doesn't matter. I would just be wrapping around this circle more and more. So I don't have to shoot off to infinity or anything like that. But you can bound your parameter if you want to, depending on your situation. One warning here is parametrizations are not unique, meaning if you come up with a set of equations to describe some curve or some function you're thinking about, a set of parametric equations, someone else can describe that same curve with a different set of parametric equations, and that's okay. It depends on how you were looking at it, what function you wanted that parametric curve to serve. But yeah, there's no unique way to parameterize something. In general, you can parameterize the same curve an infinite number of ways. There are some things that are very easy to work with. We understand it very well. So there are some standard parametrizations, and I will talk about that later on. But in general, you should know that parametrizations aren't unique. You can actually talk about the same parametric curve in very different ways. Now, I just want to show you an example of what it would mean to sketch a parametric curve. So here's an example of a parametric curve. X equals 2 minus t and y equals 3 plus 2t. And my t is bounded between 0 and 1 inclusive. Okay. So again, we're going to start from the very basics. So we're going to do something which, since Calc 1, it's not wrong, but it's kind of frowned upon if you do it. People kind of look at you weird. I'm going to show you how to graph this by plotting points. No one graphs like that anymore. But then I'm going to also show you another way about eliminating parameters. So yeah. So let's do the plotting points way. So very basic. So what you can do here is you just actually track your parameter. You can track it in a table, say. And you can plug in some numbers. Now, of course, t equals 0 and t equals 1 would be the endpoints, but I can plug in something in the middle. So, I mean, just to illustrate the point here, I'll just do one other point. So let's say t equals a half, right? So I pick a bunch of values for the t, right? Because essentially your parameter here is now the independent variable. And you think of your x and y as functions of that guy. So we're changing the t's and then we're seeing how the x and the y respond. So if I plug in t equals 0, my x is 2 minus t, so my x would be 2. And if I plug in t equals 0 into the y, my y would be 3. So this would be, because this is the lowest value for t, this is the initial point. This is where we're starting. And of course, since my t goes up to a maximum of 1, this would be the final point. All the other points are intermediary. They just help me sketch the curve, right? Notice that if I did plug in t equals 1, I would get x equals 1, and I would get y equals 5. If I were to plug in t equals a half, I would get x equals 2 minus a half, which is 1.5, 3 over 2. And I would get y equals 4. So what you've noticed here, we've gotten a bunch of coordinates, right? So from this, I got the coordinate, well, 2 comma 3. From this, I got the coordinate 3 over 2 comma 4. From this, I got the coordinate 1 comma 5 to bring it back to the x and y universe. So I can actually sketch this now based on just me plotting these points. Someone's coming in. Okay. So I know my initial is going to be 2 comma 3. So here's my initial point. Then when I plug in t equals a half, and I know the final point is actually going to be, let's say 1 comma 5. It's going to be up here. And when I plug in t equals a half, I get 1.5 comma 4. So there's going to be a 4 somewhere. And so my parametric curve is just the curve connecting those points. Okay. So this here is going to be your initial point. This here is your final point. Which at this point, too many puns. Okay, at this point, it's worth me actually mentioning something very important. Notice here, in addition to just sketching this, which it looks like a straight line, as you can tell, which again kind of makes sense because your x is changing according to a linear equation and your y is changing according to a linear equation. Your x and y look like the equations of lines, kind of like mx plus b, but instead of x now we have t. So x and y are changing according to straight lines, so it kind of makes sense that when they come together, they will form a straight line. However, so there's an additional connotation here that I want to point out. There's an additional connotation. And that is direction. Where am I going in life? Right? Notice if I were to just tell you the equation of this line, I just told you an equation of a line. I just pretty much told you how points would arrange themselves together. However, in this situation, when I'm thinking of the lower point as an initial point and the upper point as the final point, now I sort of tell you sort of about a start and an end. It seems now I don't just have a straight line, but I have a straight line with this sort of induced direction. This orientation is sort of put on my curve. I can just sort of imagine that I'm not just on a straight line, but I'm traveling on that straight line in a very particular direction, right? So you can see that you can kind of imagine that I'm moving from one point to another. So this is another unique benefit of parametric equations. You'll notice this when we had trigonometry, right? When your x was cosine and your y was sine, we thought of the counterclockwise direction as the positive direction, or the way you would go around a circle, or we naturally measure angles by moving how they open counterclockwise. And why was that? It's because of this. If you went through cosine and sine and you started plotting points of the circle, you'll notice that the points you're plotting are going around counterclockwise. So it just makes sense. Hey, let's just make angles be measured counterclockwise, right? Because there's an induced direction, right? So not only can a parametric curve just be a curve, but there's kind of a flow that's associated with it. And I mentioned earlier that there are no unique way to parameterize a curve. And that's because someone can look at this same line, but they'd want to travel in the opposite direction. And so they'd have to come up with a different parameterization to get that to work, right? So you might want to change the direction that you're traveling around a curve. And that's one of the ways you can actually change a parameterization to affect that. So here, there's also some sort of induced direction, which is a nice little thing. That's going to be useful, especially later and for things like physics and so on and so forth. So not only do we want a curve, we want to actually talk about a direction that we're moving along a curve at the same time. If you want that functionality, then a parametric set of equations is the better way to describe a curve. You would not want to describe it as a scalar equation. Okay? So this is one way, and that's just straight up plotting points. Think of the parameter as the independent variable, plug in some random values, see how your x and y respond, and from that you can plot coordinates. Here's another way you can get a curve. Which it's called eliminating the parameter. And especially in a regular calculus sequence, this is often going to be the preferred method. That's because in a class like Calc 2, Calc 3, etc., we're going to be talking about very standard things where we kind of know how the parameterization works out. So it will be easier for you to figure out what a curve is based on eliminating the parameter. In real life, though, you'd actually just tell a computer to plot points. But in class, the more efficient ways most of the time will be by eliminating the parameter. And this basically just means going from the parametric equation back to the scalar equation. By eliminating the parameter. So how would something like that work? So here we had x equals 2 minus t, y equals 3 plus 2t, and we know our t went from 0 to 1. What I can do from that is pick one of these equations and I can solve for t. So let's say I pick the x equation. Notice that my t would be equal to 2 minus x. And I can plug this into the second equation. So the first equation gives me, if I plug this into the second equation, I would get y is equal to 3 plus 2, but my t is 2 minus x. So then I would get 3 plus 4 minus 2x. And I would get 7 minus 2x. And look at that. That is a scalar equation. It is actually, in fact, a straight line. So what I can do now is I can just graph that how I always did. So now I pretty much put this situation back into a comfortable situation by eliminating the parameter. So I can just, through substitutions, plug equations into the other until I get a final equation that does not have the parameter. So now I know I have a line where the y-intercept is 7 and it has slope -2. However, again, I would definitely plug in to make sure what part of this line is the curve that I actually care about. So now I want to find the endpoints. So for initial, I would plug in t equals 0. So I know my x equals 2 and my y equals 3. And then I would plot that on here. And then my final, this is t equals 1. So I know that my x would be 1 and my y would be 5. And then I would plot that here. And so now I know the part of this curve that I care about is just this section right here. And again, because this is known as the initial point, and if I just keep track of who's the initial and who's the final, I can again see a direction induced along this curve. Right, so that's called eliminating the parameter. Right, so you can get to.
Sorry, if this were unbounded, like if it went from -infinity to infinity, how would you determine direction of the new like scalar equation?
Right. So that's actually a good question. So if t was from -infinity to infinity, right? So that means you'll actually get the entire line, right? So that's the first thing. So now you want to think, what way would you do direction? Well, naturally, the convention is to parameterize things in such that you move in the direction of the parameters increase. So you'd actually move in the direction of the increase of t. So if you had t goes off from -infinity to infinity, what you will do is you just plug in 2 random values for t, and you'll just come up with the lowest value for t gives you the pseudo initial point. The highest value for t gives you the pseudo final point. They're not actually the initial and final point, but they told you, oh, you must be moving from this point to that point. So so that was actually good. So let me actually write that down. If we had t goes from -infinity to infinity, of course not inclusive. Let me put this down. Then we'd get the whole line. So we'd have the entire thing. And in this case, to figure out the direction, and in this case, to figure out direction, plug in to random. I mean, it's random, but of course you're going to plug in some nice numbers like t equals 0 and t equals 1 or whatever. Whatever would be nice to plug into your thing. So if you have like a lot of trig functions, you might decide, let's plug in t equals pi over 2 and t equals pi, or t equals 0 and t equals pi. something like that. Pick some nice numbers, 2 random nice values for t. Direction by convention is the direction. And by the way, sometimes this is called the positive direction. Is the direction of increasing t. So the lower t value can be thought of as a starting point. Right. So you just pick 2 random values and see, are you going in which direction you're going in? And if you want to go in a certain direction, which that's going to be very, very important eventually. Eventually, the direction you're going around the curve is going to be super important, but that's going to be like in multi-2. In multi-1, I don't think you're going to be in situations where you need direction. But to be viable in a subject like physics, for example, orientation is very important because a lot of times we're going to be using curves to describe the direction of an electric field or a magnetic field or something like that. There are times when the direction is super important. And so when you parameterize something, and you can test what direction it's going in by just plugging in 2 values, and it will move from the smaller to the larger value. And then you might say, well, that's not the direction I want to go in. And then you just know to parameterize it the other way. But yeah, that was a good question. I'm not sure if I put that in the notes somewhere, but if I did not, I wrote that out just in case I didn't. But yeah, we normally think of parameterizing in the direction of the increasing parameter. So yeah, like I was mentioning with the circle, you can just, your angle can go from negative infinity to infinity, right? It just repeats every 2 pi. All the values get repeated. But on the, how do we know that we want to measure the angle counterclockwise? Well, you'd realize that when you plug in theta equals 0, you're on the positive x-axis. And then when you plug in theta equals pi over 2, you're on the positive y-axis. So clearly you're moving in the direction from the positive y-axis to the positive, from the positive x-axis to the positive y-axis, or maybe the image is flipped. And so that tells you, oh, I moved the opposite direction of the clock. Measuring the angle counterclockwise makes more sense. Okay? Now, there might be situations where you want to go clockwise, but like I said, I don't think you'll seriously consider such a situation until multi-2, which I don't even know how many of you need to go that far. Like I said, I think if chemistry majors, physics majors, math majors, I think you definitely want to go up to at least differential equations and linear algebra. Biology majors, you can get away with only doing like Calc 1 or Calc 2. So if you're like in the biological sciences, you would do Calc 1, maybe Calc 2, not necessarily Calc 2, and statistics and probability would probably be where you want to go. But everyone else, I think you should do up to multi-2 if you're in the sciences or engineering, for sure. So here's another example. We're going to sketch this. X equals 2t plus 1 and y equals t squared. And here I'm not putting any restriction. So let's just actually do that here. And how would I do this? Well, at this point, you'll have a lot of options, but because it's eliminating the parameter is going to be the nicer one. Why? Because this kind of thing allows me to go back to a situation where I'm more comfortable, essentially, right? So I know how to use something that I already know how to do to solve this new thing. So what I would do here is x equals 2t plus 1. This means that my t, I can think of this as x minus 1 all over 2. This means my y is equal to t squared. So my y is now going to be x minus 1 all over 2 squared, or it's going to be 1/4 x minus 1 all squared. So I know that this is the curve I want to draw. So that, of course, is just a parabola shifted 1 unit here, and then it goes like that. If I want to find the y-intercept, I know I just plug in x equals 0. So that would actually give me 1/4. Now, if I wanted to figure out direction, what would I do? So now to figure out direction, how am I traveling along this parabola? Am I traveling towards the right or to the left? Um, 0 and 1 seems like nice numbers to try again. So I would say t equals 0, and this is like my fake initial point. And let's say t equals 1 is my fake final. So here my x would be, if t equals 0, my x is 1, and my y is 0. So that would put me right here. And if t equals 1, my x would be 3, and my y would be 1. So that would be like pick a 3 here and go all the way up here. That's at like 1. I'm just picking a random number, random point on the thing. So clearly now I can induce the direction this way. Notice this was my initial. It's not a real initial, it's a fake initial because it goes all the way. This is the fake final. So I know I'm moving along this guy in this direction. So you might just want a parabola, but you might also want a parabola that represents also a direction of flow. I'm flowing along this curve in this direction specifically. And when you want to say that, representing instead of writing this as your equation, it would actually be much better to write this set of equations to describe that scenario, right? I don't just want the parabola. I also want to talk about the direction in which I'm moving along this parabola. Okay. Now, you've probably noticed some things at this point where it was kind of, things kind of were obvious, because here when your x was linear and your y was a quadratic, you got a quadratic. When your x was linear and your y was linear, you got a line. So there are some patterns here. So let me just mention it. Right, so here are some patterns. If your x is linear and your y is linear, you get a line. If your x is linear and your y is quadratic, you'll get a parabola. If your x is a linear function of cosine and your y is a linear function of sine, you'll get a circle or an ellipse. And so these are things that, so if you let x equals some like cosine and y equals sine, you get a circle of radius 1. If you let x equals 2 cosine and y equals 3 sine, then you would get an ellipse, right? The y's will be stretched more than the x, et cetera. So yeah, you can actually get various kind of curves by just knowing that what kind of functions am I combining here? That being said, there are standard ways to go about certain things. So this is the standard parametrization of a circle, okay? So if I have a circle x minus h squared plus y minus k squared equals r squared, and I wanted to write that as a parametrization, it turns out that a very standard way to parameterize one go around this circle is to say x equals r cosine theta plus h, y equals r sine theta plus k. These are standard ways. This is where you're going to start to see the link between this and polar coordinates, which is the next section, because in the next section, we just always assume h and k to be 0 in the polar coordinates case. And we'll get to that pretty soon, like what that's all about. But this is actually a standard way. Now, why is this a parametrization? Notice that if we have there are actually several ways to show this, but this direction is going to be the harder direction to prove it, but it's the one that's a little bit more insightful, I think. So that's why I'm doing it this way. What I can do is I can divide both sides by r squared, assume my r is not 0. And so here we just think of some functions that I can replace these guys with that would work in this equation. So here I have the sum of squares equal to 1. And so now you start to think about, well, what can I replace this with that's nice? And then cosine and sine come to play because I know that cosine squared plus sine squared equals 1. So what we can do is we can replace this entire thing with a cosine and this entire thing with a sine. And so what we would get then is x minus h over r is equal to cosine of theta, which if you solve for x now, you get r cosine theta plus h. And then you would get your y minus k over r equals sine theta. Gives you y equals r sine theta plus k. Right? So it's a very natural way to parameterize things. I do want to point out that you would get an ellipse if you were to vary the r. So let's say the coefficient that you put on the cosine is a and the coefficient you put on the y is b. Then if your a is not equal to b, but they're both like positive numbers, well, I should have said positive. Although technically it could work in general. Never mind. Then you would get an ellipse because your r would be a different length in one direction than the other direction. And so you get this kind of stretched out circle, right? So this leads us into standard parametrizations that all calculus students must know. So for circles, you want to parametrize a circle, that would be the standard parametrization. So for example, if I wanted to parametrize, here I said I'm going to parametrize various parts of the circle with radius 2 and upper semicircle. Okay, so I want the upper semicircle, the quarter circle in the second quadrant, the right side of the circle. Find another parametrization for the upper semicircle. So I also want you to show that parametrizations aren't unique. Okay, so based on what I told you above, how would you parametrize this? For example, if I ask you about the full circle, what would you do? Circle of radius 2, how would you parameterize it?
X equals 2 cos theta and y equals 2 sine theta. And then you're going from 0 to 2 pi.
Right. So you can be theta goes from 0 to 2 pi. Or if you want, it could be from negative infinity to infinity. You'd actually get the same thing because it'll just retrace it. Right. So now let's say I wanted the upper semicircle. right? So I only want this part here. How do you parameterize it now?
Same thing, but stop at pi.
Right. You can actually talk about the part of the curve you want by restricting the parameter. So you can just let it go from 0 to pi. Right. Quarter circle, second quadrant. How would I describe that? Well,
Wouldn't it be the same thing just from pi over 2 to pi?
yes. Did I ask for anything else? The right side of the circle. And I guess I'm not going to fool any of you guys here. It's going to be the same thing here. How would you bound your theta?
Negative pi to pi?
Negative pi is here. So negative pi to pi would give you the bottom half.
Sorry, yeah, negative pi over 2 to pi over 2. Right?
Right. This is a situation where in something like multi-2, students will mess up here. So a common mistake at this point would be to say theta goes from, because they're used to seeing that as 3 pi over 2 to pi over 2, but obviously that makes no sense. 3 pi over 2 is not less than pi over 2. And so which makes no sense. Also, if you wanted to force someone, which there are situations in which you can, if you wanted to force someone to start at 3 pi over 2 and go to pi over 2, that would be starting here and then going that way. You'd actually get the left side. Right, so that's very important. So this is a situation where I see people mess up in a class like multi-2 sometimes. They just memorize the angles along the or around the circle to be fixed. Like the bottom one is always 3 pi over 2. No, it's not. You do want to go from in an increasing manner. So you have to find, if you want the top to be pi over 2, you want the bottom to be less than pi over 2, increasing towards pi over 2. Yeah. Okay, good. Find another parameterization for the upper semicircle. Can anyone think of that? A completely new parameterization, right? So I have x squared plus y squared equals 4. It doesn't look anything like what we've seen before. A completely new parameterization. Any ideas? Well, this is kind of a weird one to come up with on the spot, so I'll just kind of show you. It also introduces a technique that we'll want to take advantage of later, which I'll mention in the next class. Here's something that I could do. I could solve for, say, y. This will give me my y is plus or minus the square root of 4 minus x squared. And I know for the upper, I only want the positive. So here's a strange thing, which it's convenient to do sometimes. You can set one of the variables that you're currently looking at as the parameter. So what we're going to do is we're going to set x equals x, the parameter. And this means that your y would be the radical of 4 minus x squared. And then you would just bound the x. Because I want the upper parameter, I would say this goes from -2 to 2. Or to make it not look weird, like there's nothing wrong with what I just did, but some people might be like weirded out by that a little bit. You can just generically call it another parameter. So you can set x equals t. This means that your y is going to be the square root of 4 minus t squared, and you let your t goes from -2 to 2. Why would the t go from -2 to 2? Because t is x. T is tracking the x coordinate. So the x coordinate went from 2 to -2 and 2. Right? So x goes from -2 to 2. Okay, so this is a whole other way to look at a circle. You could actually parametrize the upper semicircle. And this is just to show you that parametrizations are not unique. So this gives, so an alternative parametrization would be x equals t, y equals 4 minus t squared, and t goes between -2 and 2. And this guy here is another way to look at the circle. It's exactly the same curve that I have here. So someone can parametrize it this way, and someone else can parametrize it this way. It's exactly the same curve. Like I said, there's no unique way. I will, and again, way ahead of time here, but there are going to be situations in multi-2 where this parametrization would be preferable to this standard parametrization. And especially when it comes to finding like normal vectors and surface integrals and some other stuff. Doing it this way, you're going to end up having to do some sort of cross product formula to get to a surface integral, whereas with this way, you can get to use this shortcut formula. So we're going to wrap up there. I'm going to, of course, leave the notes here so you can kind of read through it. Hopefully this topic so far hasn't been bad, right? Especially compared to what we've been coming from. Hopefully this was a lot easier. The rest of the class is going to feel a lot like this. So I would say try to read through how to parameterize line segments. We'll pick up with that next time. You can try this example. We're also going to talk about calculus of parametric equations. I'll leave these in the notes, but just so you know, I am not going to cover these guys. So I would just want you to know how to find the derivative of a parametric curve in terms of t, but you don't really have to know the other things. Arc length I'm going to cover. So you can actually try to read through that, try to get through it by Monday, and yeah, we'll wrap up there. Thank you for your time and attention. I will see some of you later on during study hall. For now, that's it. Hopefully that was okay. You guys kind of got the drift, and I'll see you guys in the next one. Ciao.